Okay, looking back at that last example, I want to make sure that we understand the difference between a chemical equation, a complete ionic equation, and a net ionic equation. So I want to go through the example that we just did and make sure we know what those three look like compared to each other. So for a chemical equation, what you're really going to have is the all of the compounds as they are as a whole. Okay, so it's just what all the compounds look like. So for our chemical equation, we had our reactants were barium nitrate, sodium carbonate, and those were both aqueous, and they produced solid barium carbonate as the precipitate. And sodium nitrate, and that was aqueous. So in just a plain old chemical equation, okay, we don't show a net ionic, we don't show ions, we just show exactly what the compounds look like, we balance it, it's just your plain old chemical equation. And then the complete ionic equation, that's where we break apart the aqueous things into ions. And from there, we get the net ionic equation, okay? So here, we would break this apart into ions. So barium ions, nitrate ions, sodium ions, and carbonate ions in our reactants. We keep the solid as a whole precipitate. And then our other product here, sodium ions and nitrate ions, okay? So then we can get rid of our spectators so that we get our net ionic without the spectators is barium plus carbonate yields solid barium carbonate. So those are the three different types of equations that we're going to see. The chemical equation, the complete ionic, which is kind of an in-between step, and then the net ionic, which shows the whole chemical reaction. So you might be asked for one of the three. Usually it's either the chemical equation or the net ionic equation, which you use the complete ionic equation to get to. All right, earlier I mentioned that sometimes gases can be produced in these reactions. Here are three commonly produced gases: carbon dioxide, hydrogen cyanide, and hydrogen sulfide. And if you want to look at some examples, so here, for example, Hi reacts with Li2S, the hydrogen and the lithium replace each other, and we get hydrogen sulfide, which is a gas. Or here, hydrogen chloride and sodium bicarbonate, the hydrogen and the sodium replace each other, and we get H2CO3, okay? This immediately decomposes and becomes water and carbon dioxide. So here are two examples of when you would see gases produced in a double replacement reaction. Okay, now we want to switch gears and talk about single replacement reactions. So as we know, single replacement reactions are reactions in which the atoms of one element replace the atoms of another element in a compound. So it looks like this: A plus BX yields AX plus B. Generally, A and B are going to be like each other. So if A is a metal, then it's going to replace B, which is also a metal. If A is a halogen, it'll replace B, which is also the halogen. We usually only focus on the cations being the ones that are doing the replacing. Now, when we look at these, okay, we're not always going to get a reaction. Metals will not always replace another metal in an aqueous compound, and it has to do with how reactive they are. So we use this chart called the activity series of metals to determine whether a reaction will occur or not, okay? So in order for one metal to replace another metal, it has to be higher than the other metal on the list. So for example, sodium will replace zinc, okay? But zinc will not replace sodium. So if we were to put zinc in a solution of sodium chloride, nothing's going to happen because zinc is less reactive than sodium. So sodium wants to be bonded more. So that's our rule with our activity series. For a reaction to happen, the metal has to be higher than the other metal to replace it. Now you'll notice that we also have hydrogen on this list right here. Hydrogen usually acts like a cation, and hydrogen can be replaced by any of these metals that are above it. So we'll see what that looks like in our examples on the next page. Okay, so here we go. We have iron plus copper sulfate. So the first thing we want to do is find out, will iron replace copper? So we go back. Where's iron? It's right here. Copper is way down here. So iron is more reactive than copper. So yes, the reaction will occur. Okay, so then once we know the reaction happens, then we can write our products. So here we go. We want to write our product. So we know that the iron is going to come in here. It's going to kick the copper out. So we're going to get solid copper as one of our, that's a solid, as one of our products. And then the iron is going to react with the sulfate. Now iron can be +2 or +3. Usually you'll be told in that particular example to know which one to use. Here we'll use iron 2. So iron has a +2 charge. Sulfate has a -2 charge. It becomes aqueous. Okay, so there you go. That's our balanced equation. Iron plus copper sulfate yields copper plus iron sulfate. Okay. All right, let's look at our next example here. Zinc plus HCl. So here, this is where we see our H acting as the cation. So we need to know, will zinc replace hydrogen? So we need to go back to our activity series. Will zinc replace hydrogen? Yes, it will. Okay. So now we want to figure out our products. So if zinc is replacing hydrogen, okay, when hydrogen gets kicked out and it's by itself, what is it? Hydrogen is a gas when it's by itself, and we write it as H2 gas. Remember, it's diatomic, so we're producing hydrogen gas. And then the zinc is going to bond with the chloride. Zinc has a charge of +2, chloride has a charge of -1, so ZnCl2, and it will be the aqueous part, and then we balance it with a 2 right there, okay? So that's what it looks like if you have hydrogen as a cation. All right, third example, magnesium plus calcium chloride. Okay, so will magnesium replace calcium? Well, we need to go back. Let's see. Will magnesium replace? So here's magnesium, and calcium is above it. So no, magnesium will not replace calcium because it is less reactive. So we say no reaction. Nothing would happen in that particular reaction. That's it. Okay. So that's what our single replacement reactions look like. We'll be predicting products in class for both double replacement and single replacement.